We have this water tank in which the water is filled to a height h. And at the bottom we have a tapered nozzle which is fixed to the tank. Initially, the area of that nozzle is A, and then it gradually narrows down and that area becomes S. So water will of course come out of this nozzle. We need to find the horizontal component of the force tending to pull the tube out of the tank. So you can imagine that the pressure inside is of course more than the pressure outside. So that extra pressure is going to try and push this nozzle out. We need to find what is that force which is trying to push the nozzle out. So when the liquid is coming out of the nozzle, the problem is a bit complicated to think. So let's just close the nozzle first and analyze what's going to happen. And then we can talk about when the nozzle is open. So if the tube is closed shut, force on the pipe water system are shown as follows. So we have shut the tube at the end, and we are considering both pipe and water inside as the system. So the system is at rest, and what are the forces on the system? On the left side we have P in into area on this side. From right side we have P naught into area. The fact that it is tapered doesn't matter. If you just view from the right side, the cross-sectional area is still capital A. So the force from the right side is still P naught into A on this system. Or actually, if you are confused by that, you can just consider this air also in the system. Then I guess it is easier to think. So you have this liquid, pipe and air as the system. So the boundary is defined by this dot. So of course on this boundary, from the right side we have the force P naught A, and from the left side it is P in into A. Now there is one more force that is at the joint. So let's call that a reaction force, and that let it be F. That will be inside because P in is greater than P naught. This whole system is at rest. So to balance the forces, F must be inside. So that is the force that is holding this system in place. So again, let's read. If the tube is closed shut, forces on the pipe water system are shown. So these are the three forces. And since the momentum of the system is 0, which is a constant, so we can say F net is equal to 0. What is F net? It is towards right, the net force will be P in into A minus F minus P naught into A is equal to 0. Which gives F is equal to P in minus P naught into A. So they have not asked it, but if the nozzle was closed and they had asked find the horizontal component of the force tending to pull the tube out, our answer would be this. So this is so you understand what's happening, which is the force that is trying to push this out, and what is the force that they are asking. So if the force that is tending to push out is what we need to find, and that is countered by this reaction force. So what they are asking is actually the reaction force at the joint. Alright, now if the tube is open, so again we are going to consider this system, same boundary. So the external force on the pipe water system are still these three forces. From inside we have P in into area, from right side we have P naught into area, and then we have a reaction force F, which we need to find. Now this F is different than this F. Why? Because here the momentum was 0. So we could write these three forces were balanced. But here the forces are not balanced because the system has a momentum. So that's what we have written. Because the velocity of the flux here is higher than the velocity here, so net momentum of the system is towards right. So let's read that. But momentum of system is not 0. So here momentum of the system was 0, which was a constant, but here momentum of the system is not 0. As velocity of water at entrance of pipe is different than at exit. Here the velocity at entrance is 0, velocity here is also 0, so net momentum is 0. net change in momentum is 0. But here, the velocity here is different than velocity here. So there is a change in momentum because mass flow rate is same, but velocity are different. So we can now write our equation that F net is equal to rate of change of momentum. And what is F net? So towards right, it is P in into A minus F minus P naught into A. So from here, we get F is equal to P in minus P naught into A minus dP by dt. So this F is what we need to find. Just like, so it's the same reaction force which we had here. But of course, its magnitude is going to be different. Now let's see how we are going to find this. So this is what we need to find. This is the reaction force. So you can see we have the term of P in, and we have a term of dP by dt. So how we can find P in? So you can imagine we can use Bernoulli to find that. And dP by dt, that you can imagine we can find by the flow rates. So let's start writing our equations. So first, let's find the velocity here. So Bernoulli between 1 and 3. So we do that and we get V3 is equal to root 2 GH. Then we can write continuity between 2 and 3. So we get the velocity of 2 with respect to in terms of velocity of 3. So V2 into A is equal to V3 into S. So this gives V2 is equal to root 2 GH S by A. Now we are going to use Bernoulli between 2 and 3 so that we get the value of P in, which we need here. See, that's why we needed V2, because when we use Bernoulli between these 2 points, we need the values of V2 and V3. So that's what we found first. Now that we have V2 and V3, we are going to use Bernoulli on these 2 points so that we can find P in. So P in plus half rho V2 square is equal to P naught plus half rho V3 square. We'll put the values of V3 and V2 here. And okay, I'm not going to put it here. I'll put it at the end. Let's write it like this now. So P in minus P naught, which we wanted, comes to be this. Now let's talk about dP by dt. So that is change in momentum. So we can write that is the momentum here minus momentum here, because we are talking in x direction. Forces also we wrote in x direction. So dP by dt towards x direction is dm into V3 minus dm into V2 by dt. Why dm is same? Because whatever mass gets introduced in dt time, same mass leaves in dt time. So dm is same. Only velocities are different. So this becomes dm by dt into V3 minus V2. And we know dm by dt mass flow rate is equal to rho into volume flow rate. And volume flow rate is velocity into area. So again, if we talk about point 3, volume flow rate will be S into V3. So dm by dt is rho S V3 into V3 minus V2. So now you have seen we have got the term of P in minus P naught. And we also got the term of dP by dt in terms of V3 and V2, which we have already known, derived. So let's put those 2 and 3 in equation 1. So putting 2 and 3 in 1, we get the required force, reaction force at these joints to be this. Now let's put the values of V3 and V2 here. And if you simplify that, we are going to get our answer, that is rho GH by A minus S whole square. So this is the force which needs to hold this nozzle so that it does not escape. This is the reaction force in x direction. All right.